So today's lesson is going to be on graphing rational functions. And in addition to working to find holes, vertical asymptotes, x and y intercepts, we're also now going to talk about how to find a horizontal asymptote. And then we're going to end up graphing 3 examples for the notes today. Okay, so a horizontal asymptote, or vertical asymptote rather, let's start there. We said in last class we can never cross a vertical asymptote. It is a domain restriction. So a horizontal asymptote is a horizontal line in the graph that the function approaches as x gets closer to infinity and negative infinity. A rational function can have at most one horizontal asymptote. So as we looked at yesterday, we noticed that vertical asymptotes, we can have 2 vertical asymptotes, sometimes up to 3. We can have many vertical asymptotes since those are domain restrictions. But a rational function can cross a horizontal asymptote, but will always approach and never touch the asymptote as x gets closer to positive and negative infinity. So horizontal asymptotes, HA, we're going to abbreviate them as, the graph can cross a horizontal asymptote, but primarily that horizontal asymptote will, or the graph will cross a horizontal asymptote closer to the origin, and then when x gets really, 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 really big, it's going to approach that horizontal asymptote but never touch. Or if that x value gets really, 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 really small, it will approach the horizontal asymptote but will never cross out there. So to find a horizontal asymptote, it's a little tricky. We need to know what the degrees of the numerator and denominator are of the rational function. So we have to ask ourselves, is the degree, for number 1, is the degree of the numerator less than the degree of the denominator? And if it is, then we have a horizontal asymptote at y equals 0. So think of the parent function. So yesterday we talked about 1 over x. That was our parent function for a rational. Notice how we had a horizontal asymptote at y equals 0, and the degree of the numerator was 0, but the degree of the denominator was 1, making the numerator degree less than the degree of the denominator. So if you think back to the parent function and knowing that it has a horizontal asymptote at y equals 0, that can be a helpful trick for you to kind of think about. So if the degree of the numerator equals the degree of the denominator, and a is a coefficient of the numerator, and b is the coefficient of the denominator, so if we have p of x over q of x, then what we're going to do is take the ratio of the leading coefficients. So we're going to look at this and do a few examples of that in the next slide. And then if the degree of the numerator is greater than the degree of the denominator, we won't have a horizontal asymptote. We can sometimes have a slant asymptote, which is like an equation of a line, so it's not fully horizontal. We could have an asymptote that's kind of on a slant. We're not really going to be talking about those, but it's important just to know how to find all of these. But we express the horizontal asymptote as an equation of the line y equals 0, or y equals a number. In the same way we found a vertical asymptote is an equation of the line and x equals a number. So let's use those rules to help us. Feel free to go back to those rules if you have any questions, but let's look at the degrees. So the degree of this numerator is 2. And the degree of the denominator is the highest degree of its terms is 2. So it's the same degree, meaning if we were to rearrange this or look at the highest degree terms, 3 and 2, we know that y equals 3 over 2. That is our horizontal asymptote. Let's look at this next one. Notice how the degree of the numerator is 1, but the degree of the denominator is 2. So if the degree of the numerator is less than the degree of the denominator, y equals 0 is our horizontal asymptote. And then finally, if we have x, looking at the numerator, the highest degree term is this. So we have the 3rd degree in the numerator. and then the highest degree is the second. So we know that there is no horizontal asymptote. We don't have any horizontal asymptotes here. Okay, so just looking at the degrees will help you. It's okay to go back to these rules to make sure that you understand how to find them. This is going to be important in finding the horizontal asymptote so we can create some good graphs. So I just wanted to briefly talk about what the difference is between a vertical asymptote and a horizontal asymptote. We've kind of alluded to it earlier in the notes and maybe even in last class. But a graph will never cross a vertical asymptote, but you can and often do cross a horizontal asymptote. Vertical asymptotes indicate very specific behavior on the graph, usually close to the origin. Horizontal asymptotes indicate general behavior far off to the sides of the graph. So I'm going to give us a little example here. We could have a graph that has a horizontal asymptote here, and the graph could look like this. Notice how at this point and this point, we are crossing the horizontal asymptote. But the horizontal asymptote indicates general behavior far off to the sides of the graph, which means if I kept going this way, here's our asymptote, keep it going, this blue line will get close to that asymptote, but it won't cross when we're getting closer and closer to positive infinity. So it can cross when you're closer to the origin. However, we need to look at its end behavior to tell you where the graph is going to approach. So now we're going to practice graphing three rational functions. So our steps that we have to first factor the numerator and denominator. Then, starting back from last class, we have to identify holes first, and then vertical asymptotes. And then determine the coordinate point of the holes. Identify the horizontal asymptote using the rules we just found today. And then find all intercepts, your x and y intercepts. And then a graph, we have to sketch the asymptotes first, sketch all of those key points, and then we're going to graph. So let's look at this function first. We can't factor anything, and we can't reduce anything, so is there a hole in the graph? We don't have a hole, but we have a vertical asymptote where x equals +2. What about our horizontal asymptote? Is the degree of the numerator the same as the degree of the denominator? Yes, and so our horizontal asymptote will be at y equals 2. Okay, so now to find our intercepts. To find our x-intercept, we set f of x equal to 0. So like we talked about yesterday, when we begin reduce or solving, notice how we end up just having the numerator equal to 0. So we'll just set the numerator equal to 0 in the future. I'm just showing us how that would look. So at -2, 0, we would have an x-intercept. And then our y-intercept, we would be doing f of 0 and do 0 plus 2 over 0 minus 2. So we have a y-intercept at 0, -1. Okay, so now we're going to graph all of these key things. First, let's start by graphing our asymptotes. So I have my vertical asymptote at 2, so it's a dashed line, and you have to graph these. And then we have a horizontal at 2. And then we have a y and x-intercept at -2, 0, 1, 2, 0, and a y-intercept at 0, -1. So we have this piece of the graph, but we have another piece of the graph. So if we have a graph down in this lower area, we will always have a graph opposite it in this upper area for the examples that we will look at. There are some more complicated rational functions that could differ, but let's see if this graph will follow that trend and be up over here. So the only way for us to do this by hand is to see or pick x values rather. So we have 1, 2, 3, 4, 5, 6. So we could pick 3, 4, 5, or 6. So find f of 3, f of 4, f of 5, f of 6. So what if we found f of 3? Let's see what that looks like. So we have 3 plus 2 over 3 minus 2. So we get 5 over 1, which is 5. So we know that we have a point on the graph at 3 comma 5. 1, 2, 3, 1, 2, 3, 4, 5. So for our graphing purposes, I'm okay with you just graphing one of those points just to verify that's where the graph is, the other piece of the graph is located. And then we can draw in another piece and show that it's going to approach the asymptotes. So this is a key part here. You could have picked f of 4, f of 5, f of 6, but it's important for you to actually do the math to get one point in that opposite side. If, let's say, you're finding your x-intercepts and y-intercepts, and one of the intercepts is on the left and the other intercept is over here, and we have points diagonal each other, then you don't need to do this, but you're going to have to find points if you aren't sure what the graph looks like. Let's look at this next one. So here we can factor, so I'm going to factor out an x. And then the denominator, we have x plus 2, x plus 3. So notice here how we have a hole in the graph. So we have a hole where x equals -3. So the reduced function is x over x plus 2. So if we plug in -3 for x, we have 3. So we know that we have a hole at -3 comma +3. Okay. All right. So we practiced that a little bit yesterday, but now look, we have this remaining factor in the denominator. So that represents our vertical asymptote. So x equals -2. The degree of the numerator, if we look at the original problem, is the same as the degree of the denominator. So for our horizontal asymptote, we know that y equals 1 over 1, or 1, because those were the coefficients. And now to find our x-intercept and our y-intercept, let's see. So to find our x-intercept, we'll set the numerator, the reduced numerator, equal to 0. And look, we just have x, so we know x equals 0. So we have 0, 0. There, 0, 0 as an x-intercept. So therefore, what do you know your y-intercept is? 0, 0 as well. Okay. All right, so now let's get to graphing. So we have our vertical asymptote at x equals -2. Okay. Our horizontal asymptote at y equals 1. All right. And then we have 0, 0 here is this piece. And then we have -3. So 1, 2, 3, and then +3. 1, 2, 3, and we have a hole in the graph. So it's going to be an open circle. Now notice you have points on both sides. So what you can do is just draw in this piece and draw in this piece, showing that we are approaching the graph. So again, going back to the previous problem, we did not have points on both areas of the function, but now we do for this particular problem. So you can graph that whole open circle, and then we can graph the x and y intercept at the origin, and then plot the rest of the graph. All right, let's look at one last problem. So if we factor the numerator, which is already done, we have x plus 3, and then, whoops, and then we have x minus 7, x plus 3. So here we go, common factor. So we have a hole in the graph at -3. So if we plug in -3 to the reduced function, we get -1/10, so something really tiny. So we'll have to eyeball this when we're graphing. That's okay. And then our vertical asymptote is x equals 7. It's that remaining factor in the denominator. Horizontal asymptote, notice how the degree of the numerator is less than the degree of the denominator, so y equals 0 is our horizontal asymptote. So if y equals 0, let's just think about this, is our horizontal asymptote. Can we have an x-intercept? We could, but if we set the numerator equal to 0, notice how we just have a 1 left after we've reduced this fraction. We have a 1 up there. So no, we won't have an x-intercept for this graph, but will we have a y-intercept? If we set do f of 0, we're left with 3 over -21, which is -1/7. So at 0, -1/7, we'll have a y-intercept. So let's now graph everything. So vertical asymptote at x equals 7. So 1, 2, 3, 4, 5, 6, 7. Okay. And then we have -3, -1/10. 1, 2, 3, -1/10. So we have a point right there. I'm going to eyeball it. And then we have 0, -1/7. So notice how we have this graph on this side. So we can actually draw and connect these 2 points and eyeball this so it's not touching that vertical asymptote. But now we have to find a point over here. So when you pick a point, pick 8, 9, or 10. Okay, if you picked 8, 9, or 10, find a point over here so that you can draw in the rest of the graph.